Okay, I would like to introduce Alexander Leong from Boeing about efficient constrained optimization. Thank you.
All right, thank you. Uh, yes, so today we're going to talk about a type of mathematical optimization, constraint optimization. So just a brief recap on what constraint optimization is. We minimize some function f naught of x subject to some equality and inequality constraints given by fi of x less than or equal to bi. So this is the objective function, and these are the constraints. To solve these type of problems, typically they employ what are interior point methods. And solving nonlinear problems typically involve some finite difference scheme or automatic differentiation for computing gradients and Hessians. So ConicSolve is a conic optimization solver. The difference for this type of solver is similarly we have this what we call a cone quadratic program, and these functions are given by matrices and vectors. So the variables here are p, x. X is the variable that we're trying to solve for. C is what encodes the objective function. We've got G, and which are the inequality and equality the inequality constraints are given in G. A gives the equality constraints, and then we've got these other vectors H and B that go together with these constraints. This S is just an internal primordial variable that's used by the solver. So X is parameterized by this cone K, and there's various different types of cones defined in this package. So we've got the non-negative orthant, second order cone, and positive semidefinite cone. So the non-negative orthant typically used in linear programming. So by manipulation of these equations, you can construct a linear program and various other programs. Looking at the positive semidefinite cone, that is used for semidefinite programming, which we'll cover soon. So what makes cone programming interesting is the expressiveness of conic optimization. So this diagram depicts the various subsets of optimization problems that you come across. So QP is basically, LP is a subset of QP, which is a subset of SOCP and SDP. And cone programming is basically a way to encode a lot of these different cone programs. Another interesting program here that we're going to look at is sum of squares programming. And that's interesting because that can reduce to semi-definite programming to what are called relaxations of the non-convex problem. What we're going to do is we're just going to assume that everything is convex because that's what's easy to solve, and you get a lot of benefits by solving convex problems. So this slide is basically just summarizing what I've described. So key message here is basically manipulating those matrices and vectors allows you to express these different problems. And ConicSolve is written purely in Julia. And I know there's a lot of different optimization solvers already written in Julia, but what makes ConicSolve slightly different is it employs this Nesterov-Todd scaling, and it focuses on what are called symmetric self-dual cones. And the reason for this is for applications that require high order accuracy and numerical stability. If you've worked with something like Sudumi or Mosaic, they employ similar type of methods for solving these problems. But as you may know, Sudumi is implemented in MATLAB, and Mosaic is a proprietary solver. So I went and decided, okay, I think we need something open source in the mathematical optimization community, and hence this package. So the mathematics around these cones is using what's called Jordan algebra, and that allows you to construct these symmetric factorizations of the gradients and Hessians. And by doing this, you don't need to, it just means that you have to work with the different cone types. You are basically restricted to that, but you know, it's necessary in order to get those performance benefits that I've described. Yep, so I covered that one. So one way to understand what a solver is actually doing is having a geometric perspective of it. This blue line sort of shows you the path that the solver takes. So it's, you know, we start at some initialization point here, and then after many iterations of running the solver, you get closer and closer to the optimal solution. Obviously, the minima of this function, this is quadratic function, is at 0, 0. And these lines here are basically the half spaces that define the constraints that need to be satisfied. So we see that it starts off in some infeasible region, but as we minimize those residuals, we get closer and closer to something that's feasible and optimal. And that's what we expect here. The solver performance. So when you're using a solver, or any solver for that matter, you might get some console output that looks like this, tabular form. You've got, in this case, dual residuals, primal residuals, the centrality, complementary residuals. You got this duality gap, which is the difference between the primal objective and the dual objective. And you've got the primal objective reported here. So for these 3 columns, you want all of these to come down to 0, and that's what we sort of see here. And then this gap, we want to get to 0 as well. And by having all of these 0, we satisfy the optimality conditions, and that allows us to be confident that we are at an optimal point and one that is feasible. If you do not meet those certain tolerances, then sometimes the solver would report this status back, in this case a dual infeasible flag. This one, these plots here show the path that the solver take in terms of the residuals over iterations, and we see that polynomial convergence to 0, which is great. Let's take a look at some applications of how we use ConicSolve. One is maximum flow minimum cut, which is can be formulated as an LP problem. And we've got this graph here that sort of illustrates what we're trying to optimize. So these numbers show the maximum flow and minimum flow that that are constraints on this graph here between the nodes. And we can encode this in a matrix G. So the rows and columns give the weighted edges in this graph. On the right here, we can see the code that is required to define this optimization problem. In this case, instead of defining those matrices explicitly, what I've done is written functions to construct those matrices. So that reduces some of the tediousness in defining those optimization problems. Okay, so here's a technique that I use to convert those functions that encode the problem into matrix form. And an example of this in maximum flow is the flow conservation constraints. So flow conservation means the sum of flows into a node equal to the sum of flows out of a node. And here, what we're trying to solve for are the flows given by x, and this can be vectorized via one example is this scheme here. The technique is basically figure out what x represents, and then the equations would define themselves. Okay, so with the max flow min cut example, once we've defined those matrices and vectors, then we can write some function here to give us the objective, and then what we do is we pass it into the solver. So here we construct the problem, we give it the parameters and the cones. So the cones with respect to the variable x, and for because this is an LP problem, remember we use the non-negative orthant over the variable x. Let's look at a different example now, which is a bit more involved. So phase retrieval, what we want to do is for a 1D signal, we want to figure out what the phase is. And whenever you're trying to estimate, given some measurements of that 1D signal, we have to try and reconstruct that signal from some form in order to measure that reconstruction accuracy. So here A is defined as this 1D DFT matrix, and A is also what we use to solve this problem is this random illumination filter. So basically we just sample a bunch of points from a Gaussian distribution, and then that would construct this matrix A. And by doing so, it happens that we achieve perfect reconstruction for high probability of signals. And there is lots of applications of doing this. Okay, so something that's in image processing, rank minimization. Again, it's a SDP problem. We want to minimize the rank of a matrix. However, this is a non-convex problem, so what we do is to minimize the trace, and that's a good way to relax this. So minimizing the trace of this positive semi-definite matrix X, subject to AX equals B, and then enforcing that positive semi-definite cone on the variable X. Here, I've added an additional constraint where all the entries are non-negative. So I've added also a non-negative orthant constraint on X. So the code looks like this. You can see I load the image here. This is a pretty expensive operation, so I do it patch by patch. So those are the coordinates given here. Construct the block matrices, denoise the image, and then pass it to the solver. And what we need to do is figure out where the image goes in this matrix X here. So we force X to take on these values in the yellow elements here. This has to be a symmetric matrix, so we just do the transpose and set those elements here as well. And all we need to do is to encode all this information is to just encode it in this lower triangular region here. What we know is that all we're really interested in are what these values are. These other values are just to fill in the matrix. And so when you run the optimization algorithm, this the trace of this matrix goes further and further down, and we get a denoised image. So it looks something like this. After 5 iterations, I just basically introduce these noisy pixels, which you can see here in yellow, and by running this algorithm, you can see that the more iterations you get, one that is close to recovering what was originally corrupted. Right, so next example, total variation reconstruction. So here again, we're given a 1D raw signal, And it's split into these two terms here. We've got one that is by the 2 norm, which is the, I think it's minimizing the difference between the signal and the one that is corrupted by noise, and we're trying to estimate the original signal. And then here, what we're trying to do with this L1 term is we're trying to penalize any significant variations in the signal itself. D is the 1D finite difference matrix. There's actually 2 ways you can solve this problem. We can see that this is an L2 norm, so naturally we might choose to use a SOCP constraint on this term, but in this case here, we can just add a square and that converts it into a quadratic program. And then we can encode that in the matrix P. So yeah, there's applications include voice recognition and data transmission. A lot of code here. Yeah, I think you can see that is a bit involved, but nevertheless, it's easy to create these matrices through functions. And you get these, a result that looks like this. You get the input signal and a reconstructed version of that signal that removes a lot of this volatility in the signal. So if you crank up lambda, you get a smoother and smoother signal, so cranking up this term here. And it only takes 2 seconds over 10 iterations, so it's very efficient. The last example is trajectory optimization. So this is using sum of squares programming, and here we want to minimize the jerk or the third derivative of a polynomial. So a trajectory can be encoded as a sequence of polynomials, which is what we're doing here. We constrain that to the sum of squares cone, and then we set some initial conditions. So we say that the initial position is 0, the final position is 5 at time equals 1, and then we set the initial and final velocities to these values here. And so the polynomial, you can have any high order polynomial, and the higher the order of the polynomial, the better is the result. So, well, not technically, but you get something that is feasible. So if you come up with, if you put in something that is too low order, you may not find a feasible solution. So you just need to increase the order of the polynomial that you use, and in order to get something that's feasible. So sum of squares programming uses this idea of the lesser hierarchy. You may have heard of that, and it also goes by the name moment SOS. So the applications of this are path planning, UAVs, and robot manipulators. Okay, so the guts of the solver is to basically solve this KKT conditions. And for this quadratic program, we want to solve this given this matrix K for these variables X, Y, and Z. So we know what K is, we know what this vector is, and the way to solve this is using a sequence of operations called the QR-Cholesky, which basically does QR and Cholesky on a lot of these terms. I'm not going to derive that here because it's pretty messy. If you look at the paper, it's pretty trivial, but it's a very effective way in having some level of numerical stability as you compute the solution vector. If you run out of memory, then you may want to look into iterative methods like minres. That's also implemented by this package here, and that falls into the set of methods called Krylov subspace methods. So things to consider, you want to consider scaling for numerical stability. the size of the problem that you're trying to solve. So I wouldn't recommend using this solver for very large scale problems or very highly sparse problems. This solver works pretty well when the problems are small and dense and where you need a high degree of accuracy. Another good thing is that because it's using matrix factorization, it's very easy to throw these to the GPU. And there's a GPU implementation of this solver as well. And you can get performance of up to 2 or 3 times faster by using that. So future work, there's a bit of additional GPU optimization required for the iterative methods that I've defined. There needs to be some integration with common optimization front ends like jump. More examples to make it more palatable to adopters in the scientific community, and just stabilizing the APIs so that it's ready for industrial applications. So in summary, what I found through this experience of developing this package is how tedious it is to define those matrices and vectors. I think one thing that the optimization community needs to focus on is just finding better abstractions for indexing into arrays and matrices, and just coming up with a language to express those constraints for any given optimization problem. Yeah, so that concludes the talk. Thanks for listening. Here's the QR code that will take you to the package. And you can read up the various documentation there. And yeah, looking forward to any PRs or any questions you may have. Thanks.
Yep. Are there any questions? Okay.
Hey, thanks for the talk. Did you do any benchmarking performance-wise against the Mosaic and the Sudemi packages?
That's a good question. I'm still yet to do that. Yeah.
Cool. And if there's no more questions, there is a keynote at the start.
Yeah, I wanted to remind everyone that at 4 o'clock, or really 4:10, in the main building, room 120, there's a keynote, another keynote. And also at 6 o'clock, there'll be the poster session. Let's thank Alexander again for a nice presentation.